the iodine pentafluoride, or as the Brits would say, iodine pentafluoride, which I will start with the iodine in the central position. I will dispose the 5 fluorines about that central position, and I will count electrons. Well, iodine and fluorine are halogens. They're group 7, so I have 5 plus 1, and I have 6 times 7 equals 42 electrons. And I will draw a line connecting the central atom to the outer atoms and deduct 2 electrons for each such bond or bonding pair. And that is minus 10 electrons gives me 32 electrons. Well, we can see now that I'm going to distribute these remaining electrons first, I'm going to distribute them to the outer atoms in such a way as to complete their octet or their closed shell demand. And we already know this is always going to be, except for hydrogen, it's always going to take 6 electrons for each of the outer atoms. I have 5 such electrons. I can electron lone pairs, and that means 5 times 6 is 30. So I'm not even going to bother to draw the freckles since I'm going to erase it in a minute, but I can deduct the 30 here. And I have 2 electrons remaining. That's what I needed to do this for. I'm going to place those on the central atom. So I'm going to end up with a structure that is going to have a 1 lone pair on the central atom, which I can now draw. We've taken care of all the electrons. Let's make sure that the closed shell demands of all the atoms are met. Well, we don't have to worry about the outer ones because I'm not even going to draw them. This is scratch paper. I'm just interested in the central atom. I've got 2, 4, 6, 8, 10, 12. Well, that is more than 8, and 8 is enough. So this is an expanded octet, and it's because we can have this with a heavier, lower in the periodic table, higher principal quantum number of what is 5th row. That's more than enough. All but the second row is the only one that can't have more than 8. So we've satisfied Lewis's demands on the closed shell configuration, and we can now start considering how many E pairs are on the central atom for geometric considerations. And I have 1, 2, 3, 4, 5, 6. Well, 6 is going to require octahedral E-pair geometry. And since there's 1 lone pair on the central atom, the molecular geometry is going to be not the same as the E-pair geometry. And that is going to be, in other words, I'm going to place this lone pair on one of the octahedral sites and draw the molecule with the other 5 atoms on the other octahedral sites. And this will give me an octahedral, well, we'll see what type of molecule results. So let's draw it that way. And I think I'll start with the iodine, and I'll place the lone pair right here. And then I will draw in this, what would be a sort of looks like an axial position now. I'll put a fluorine atom with all of its lone pair electrons. And now I'll draw in the remaining octahedral sites what would turn out to be, what would now be an equatorial plane. The remaining fluorine atoms, their lone pairs. end up with what would be, I've got octahedral E-pair geometry, but I have, not wipe off, I have what we would call a square pyramidal molecular geometry, the geometry of the remaining atoms. The molecular geometry is of the geometric arrangement of the atoms in space, and the E-pair geometry is the geometry of all the pairs of electrons, and we're particularly interested in the central atom. So we're now done as far as drawing the molecule is concerned. Now there is no resonance demands based upon this. So now what I need to do is assign the formal charge, and the formal charge is going to be, let's take the atom. There's only two types of formal charge. And the atoms are going to have an iodine, and the iodine I have 1, 2, 3, 4, 5, 6, 7. That's 7 electrons. It's group number 7. 7 minus 7 is equal to 0, so I have 0 formal charge assigned here. And now let's do all the fluorines, which are equivalent, so I only need to have one of them. And now I've got 2, 4, 6, 7 on each of the fluorines, and there's group number 7, so I have 0 formal charge on each of them. So we've now completed A through P. It's on the board in such a fashion that, okay, it doesn't all fit. But now I'm going to go over and do CO2. And CO2 is the last one we have to do. And I'll start with the same procedure. Start with the carbon, draw the oxygens around it, add up the valence electrons. There is 2 times 6, because this is group number 6 with oxygen, plus 4, group number 4 carbon, equals, let's see, that's 12 plus 4 is 16 electrons. So I will first draw a line connecting the central atom to the outer atoms. That takes care of 4 electrons minus 4 electrons. I have now got 12 electrons remaining. And we already know how many does each atom other than hydrogen need to give it that closed shell electron count, and that would be 6. I assigned 6 to each of the minus 12 electrons. There are none going on, no lone pairs going to the central atom, so I'll just draw it for laughs, because in this case I'm going to need to check Lewis, and the Lewis demands are not satisfied. I've got the closed shell electron count with the oxygen atoms, but I am severely deficient here on the central atom, the carbon atom. I've got only 4 electrons, so I'm going to need 2 more. So now I'm going to have to evoke multiple bonding, so I'll take a lone pair from here and place it in between the atoms. And I'll do the same thing on the right-hand side. And now I've got double bonds to each of the oxygens. They're now equivalent, and we have satisfied the closed shell electron count demands of carbon dioxide with 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. 8 being the minimum requirement. And so we're now satisfactory with the structure. Now, let me find my eraser. I'll erase this scratch paper. This is scratch paper as well, but now we want to do the electron count for the purposes of determining both the E-pair geometry and the molecular geometry. These double bonds, recall, count as one pair when we're looking at it in terms of geometry. And so I have 2 E-pairs associated with the central atom. That means it's going to require linear E-pair geometry. and there are no lone pairs on the central atom, therefore the molecular geometry and the E-pair geometry are going to be the same. So I will now draw it with that type of geometry. Voila. No, I'll actually redo it in blue so it's being consistent. This is my scratch paper. Now I go on to my test, and I'll draw the molecule. It's going to be carbon double bonded to an oxygen, double bonded to an oxygen, and with the right geometry, linear molecular geometry. And now we can do the formal charge, and the formal charge is the atom being carbon and oxygen. Formal charge is, I've got 1, 2, 3, 4 electrons. It's group number 4. 4 minus 4 is 0. And so the central atom, carbon, has 0 formal charge. Now, the formal charge on the outer atoms, I've got, they're group number 6. And I've got 1, 2, 3, 4, 5, 6. So 6 minus 6 electrons is going to give me a formal charge of 0 as well for the oxygen. So now that completes A through F on this problem. This is what I expect to see on the page. So let me readjust this one so that